All right, it is time for round 3, lines, planes, and hyperplanes. These are the infinitely extended flat objects of various dimensions. A line is the infinitely extended flat one-dimensional object. You can start at any point on a line and walk as far as you like, either forward or backward, without ever turning. A plane is the flat, infinitely extended two-dimensional object. Drop a bug somewhere on a plane, and it can set off in any direction, or its opposite, as far as it wants to go. I've drawn it with edges, but of course this is supposed to be an infinite plane. Not only can it travel in that direction, but it could, at any point, rotate 90 degrees and travel in a second dimension without ever leaving the plane, and along which it can travel as far as it likes, without any curviness along its path. Well, what about the three-dimensional flat, infinitely extended object? That would be a three-dimensional hyperplane. What would that look like? Well, we may be living inside one. After all, if you imagine a bug in the familiar three-dimensional space in which we live, it could, of course, fly off in a straight line from wherever we happen to drop it, but it could also fly off in another direction perpendicular to the first. And in both cases, we'll assume that it could fly as far as it wants. We'll assume that this is a special bug that does not require oxygen, food, or water, or anything like that, and can pass through any objects it meets along its way. We're just interested about the space in which it's operating. So now we've got two dimensions, but our bug can also fly in a third direction, which is perpendicular to both of the first two. And here too, we will assume that there is nothing in the space itself that prevents it from going on as far as it likes. And there are no bubbles or folds in the space. It just has this smooth, homogeneous ride all the way in any direction it chooses to go. It is in that sense flat. In the case of our one-dimensional flat, infinitely extended object, a line, we can see the flatness because we are looking at it embedded in a space of 2 or 3 dimensions. So we say, yeah, that's flat. It's a straight line. Similarly with the plane, we think about that plane as being embedded in a 3-dimensional space. And we say, no, there are no folds or bubbles or anything like that in it, no hills and valleys. So it's flat. We understand what that means. I can't see that with a 3-dimensional hyperplane because to see that it isn't twisting or bending in any way, I would need to be in a space of at least 4 dimensions so that I could get out and actually look at that thing. But such a vista is, of course, denied to us, wretched 3-dimensional creatures that we are. Nonetheless, we can reason about such things, and they will help us understand certain calculations. Just as we can have 3-dimensional hyperplanes, we can have 4-dimensional hyperplanes, though these are much harder to get your head around, because you can't just say, as we could with the 3-dimensional hyperplane, oh, it's kind of like the space in which we presumably live. A 4-dimensional hyperplane would be one in which our bug could not only move in these 3 directions as far as it liked and without any curving into the ambient space, but the bug could also move along some 4th dimension, some 4th spatial dimension, I'm not talking about time or anything like that here, which would somehow be perpendicular to all 3 of the preceding dimensions. Now, such a configuration is, of course, impossible in 3-dimensional space, just as it would be impossible in 2-dimensional space to have 3 lines that were somehow all perpendicular to one another. So there's no good way for me to try to represent a 4-dimensional hyperplane in mere 3-dimensional space. It won't fit, and it especially won't fit into the 2 dimensions of the tablet on which I'm drawing these things. But nonetheless, we will find it useful to discuss such things. And again, along all 4 axes, we could travel as far as we like, or at any point in the 4-dimensional hyperplane. We could travel as far in any direction, say parallel to those axes, as far as we like. They're infinitely extended and flat in the sense that the 4-dimensional hyperplane is not curved or bending when viewed from a, say, 5-dimensional vantage point. Linear algebra is really exclusively concerned with flat things, which makes all its computations much, much, much simpler than the kinds of computations you may be used to from calculus, which is all about curviness. On the other hand, linear algebra is a more abstract subject than calculus, in part because we are working with these higher dimensional objects, flat though they may be. What I want to do in this video is come up with some algebraic representations of these things. We may not be able to see a 5-dimensional hyperplane, but we will be able to write down algebraic representations that will help us get to know them. And more importantly, we'll be able to recognize when a certain line of algebra actually represents a 4-dimensional hyperplane or whatever it may be, and then bring our geometric understanding to bear on the algebra. As I've said several times now, much of the beauty and power of this subject comes from the interplay between geometry and algebra. And we are going to consider two different kinds of algebraic representations of our fine flat friends. First, we will discuss Cartesian equations for these, at least in certain circumstances, beginning with the simplest case that you first learned about probably back in an Algebra 1 class, where you learned the equation of a line in the plane. And we'll build up from that idea, from lines to planes to hyperplanes. And then once we have a good sense for those Cartesian equations, we'll switch over to parametric representations for these objects. That may be new to some of you, or it may be familiar. Anyway, let's get started by reviewing what you learned back in Algebra 1. If I have the usual set of xy axes in the plane, and I have a line in the plane, we know that we can always represent that line with a linear equation of the form ax plus by is c, where a, b, and c are constants that depend on the specific configuration of the line in question. And back in that early algebra class, you surely discussed things like the point-slope form of a line and the slope-intercept form of the line. And there are various forms you can put a line in, but it's this form where we have the x and y stuff on one side of the equation and a constant on the other that we'll be using most frequently in this class. And I want to begin simply by reminding you why a straight line in the plane can always be represented by an equation of that form. Because the logic we use to get from the line to this equation is the same sort of logic we'll use to get from a plane to its equation, or from a 3-dimensional hyperplane to its equation, or from a 4-dimensional hyperplane to its equation, and so on and so forth. So let's go back to junior high school. So to be concrete, let's just say for the sake of argument that this line crosses through the y-axis at the point 0, 3. Well, there are infinitely many lines that cross through the axis at that point, but let's pick out this one specifically by identifying the line's slope. Let's say that the slope is a half. In other words, for each unit we run, we rise half a unit. So if I run 10 units, I would rise 5 units to get back up onto the line. All right, now if I want the equation of that line, if we're coming up with this for the first time in our lives, we've never done something like this before. The whole game is to say, I'm looking for some kind of an equation involving x and y, such that if I take the coordinates of any point on this line and stick it in the equation, I will get a true statement. Well, if you think about this with fresh eyes, a fresh brain maybe, you realize that this is somewhat challenging. How can I come up with an equation, a single equation, that will be satisfied by the coordinates of any of infinitely many points on this line? That seems like a tall order. Can we actually come up with such a thing? Well, yes, as you know, we can. And this is how we would reason our way to it if we were thinking about this for the first time. So let me try to come up with an equation where y is going to be equal to some function of x. In other words, if you tell me what the x value is, I should be able to tell you what the corresponding y value is. So that when x is 16, y is whatever it is. When x is minus 97, y is whatever it is there. And then I'll have an equation that is not just a I give you the output for whatever input you give me, but I'll have an equation that is satisfied by every point on this line. So let's see if we could do it. We'll start with the fact that we know that when x is 0, y is going to be 3. So let's use that as like our base camp. So I'm going to take the 3 and just put that here. There'll be more to come, but I'm going to start with the 3. So let's think about some other point on the line. This is a variable point. It can represent any point on the line. What are its coordinates? Well, I have no idea. But let's just say that the horizontal distance of this point from the y-axis is x units. Now, x might be 5 in one case, or 97 in another case, or minus 24 in another case, whatever. The important thing is that every point on the line has some x-coordinate. And whatever it is, I know how far up, or perhaps down, I have to travel from my initial value of 3, from my initial y value of 3 to get there. I know that because the slope is a half. What does it mean that the slope is a half? It means that for every unit I go this way, I have to go up half a unit. So if I've gone over x units, then I have to go up half of x units. Hey, so that's telling me something. I know the first coordinate of that point, right? That's x. So I'll write that down here. That is x. But what's the second coordinate? Well, it's y, right? Yeah, it's y, but the whole point is I want to get it in terms of x. That y value in terms of x is, look, it's the original 3 that we started at our base point, and then I have to add on to that half of x. So that second coordinate is going to be 3 plus half of x. The y coordinate, in other words, is 3 plus half of x. So I'm going to put that in my equation. And now I've got it. This represents a variable point. It can be any point on that line, no matter what the x value is, whether it's positive up here or negative down here. The corresponding y value, the second coordinate of the point, is going to be 3 plus half x. The change in height that comes as a result of moving x horizontally, because that's what the slope is telling us. And this is what your Algebra 1 teacher would have called the slope-intercept form, because here is the slope of the line as a half, and here is the y-intercept, which is 3. And then you went on to memorize that any line can be written in this form, except, of course, it wouldn't be 3.5. Any line in the plane would end up looking like y equals b plus mx, where this is the y-intercept and this is the slope. And you use that formula all the time in your algebra classes and your calculus classes. But this is one way to see where it comes from. Oh, but 2 comments here. First of all, as I said, we're taking something of this form, and I'm thinking of it in this slightly different algebraic form. Obviously, I can rewrite this in this form. I just push this guy over to this side, and I end up with minus half x plus 1y is 3, which falls into the form we have right there. And it's obvious that we could do this for whatever constants we had here for the y-intercept and the slope. Oh, but the second thing I wanted to mention, one reason why this form is a little nicer than the one I just erased, y equals mx plus b, is because this one covers all lines in the plane. That slope-intercept form covers almost all lines, but not ones like this. Not vertical lines, because they do not have a well-defined slope. Because you can't say on a vertical line, well, if I run x units, how far up do I have to go to get back onto the line? Well, you never get back up onto the line. So the slope is not even defined on such a thing. But of course, they do have perfectly good equations. Like if this guy is 18 units to the right of the y-axis, then the equation of this line is obviously x equals 18, because every point on that line satisfies that equation. They all have x coordinate of 18. And this equation is part of this form. It would just be 1x plus 0y is 18. But you can't put that into slope-intercept form. So this thing covers everything. Okay, enough with 8th grade. To summarize what we just saw, let's write that a line in R2, any line in R2, has a Cartesian equation of the form ax plus by is c. Now let's move on to the equation of a plane in R3. All right, well, here's the axes in R3, and let's say we have a plane that cuts through the z-axis at this point and comes sloping down somehow. Let's say it cuts the x-axis here and the y-axis over here, so that this stuff right here is the portion of the plane that cuts into the so-called first octant of R3. In other words, the part of R3 where x, y, and z are all positive. You have to imagine this continuing on, of course, in every direction, but this should be enough to represent the plane for us. And we want to figure out a general form of the equation of a plane in R3. And the way we came up with this equation for lines in R2 will guide us right to it. We're looking for an equation satisfied by every point that lies on that plane. But of course, these are points in R3, so they have 3 coordinates, an x coordinate, a y coordinate, and a z coordinate. So instead of thinking about y as a function of x, let's think about z as a function of 2 variables, x and y. So the idea is that if I think about any point on this blue plane, its z coordinate should be determined by its x and y coordinates. So do we have enough information to figure out how that determination actually takes place? Well, we need a little more information, just like in the case of lines in R2. Once we had the slope of the line and the point where it crossed through the horizontal axis, then we were able to write down such an equation. So let's come up with the corresponding parameters here. Let's say this plane crosses through the z-axis at 0, 0, 5, so 5 units above the xy plane. But now what do we do for the analog of slope in this case? There's not a single slope for a plane, although we can describe 2 separate slopes, an x slope, so to speak, and a y slope. See what I mean by this? Let's pick a point on the blue plane. Now it's a plane. It's flat, right? That's the common feature of all of these objects we're considering in this video. That means that if we're on this plane and we set out in the x direction, in other words, if we projected the shadow down onto the xy plane and the shadow was moving exactly in the x direction, so that our point is actually coming down the plane, maybe something like that, it's coming down along a straight line. There are no little bumps or hills it has to traverse to get there. And that straight line can be thought of as having an x slope, meaning if I think again about those projections right there, then the idea is that for every unit we run in the x direction, the z coordinate will rise, or in this case, fall by a certain number of units. And that number of units by which z falls for every unit we run in the x direction, falls or rises, that is, of course, the x slope. And for the sake of argument here, let's just say that that x slope is -2. It's clearly negative because as x increases, z is falling. And there was nothing special about the place where that point was. If we had started at some other point, well, of course, the x slope is constant. Again, that comes from the flatness, the homogeneity of the plane. It looks the same from any position. It's totally bare. It has no features. All right, but besides having an x slope, our plane will also have a y slope. And of course, you can guess exactly how that would be defined. For every unit we run in the y direction from some point, the z value is going to fall or rise in a certain different configuration of the plane. The z value will change by some fixed amount. So in this case, each unit we run, z falls by a certain amount. This is still going to be negative, but it doesn't look quite so negative. So let's just say for the sake of argument that the y slope in this case is -1/3. All right. Well, if I know this z-intercept, the x slope, and the y slope, and of course, all planes have such things, well, except one funny little counterexample I'll mention in a moment, which corresponds to the case of the vertical lines in R2. But besides that, all planes have a z-intercept, an x slope, and a y slope. And if we know those values, then it's not hard to come up with an equation for the plane. Let's do that here just by thinking about it. Let's get z as some function of x and y. So you tell me x and y, and I'll tell you the z corresponding to it. Let's do the same thing we did in the case of lines. Let's start at base camp here, where z is equal to 5. And then I will want to tack on some stuff that accounts for how far away I've gotten from the base point. Like, let's just say we're at this point we started at right here. Well, that point has a certain x coordinate and a certain y coordinate. And as we go from this point where x and y are 0 and z is 0 to this point, the projection there where we just have x and y or whatever and z is 0, we have to travel a certain distance along the x-axis and then travel a certain distance parallel to the y-axis. Let's just call those two displacements x and y, which is fine because I'm trying to get z as a function of x and y. Well, when I travel here through this displacement of x, the point on the plane falls a certain distance. How much does it fall? Well, I have to think about the x slope. For every unit I run along the x-axis, the z value falls by 2. So if I run x units, it's going to fall by 2x. And then we have this displacement of y parallel to the y-axis. When we do that, the z value falls some more. How much more? Well, we have to think about the y-slope. For every unit we run in the y direction, it's going to fall, the z component is going to fall by, in this case, 1/3 of a unit. So if we run y units parallel to the y-axis, the z-coordinate falls by 1/3 y. So now let's come up to our equation, and it should be easy to write down. At this point here, where the first two coordinates are x and y, what's the z-coordinate? Well, we started at 5, but then we had to subtract off 2x, and then we had to subtract off 1/3 y. So this is going to be z is 5 minus 2x minus 1/3 y. And lo and behold, our flat, infinitely extended object, the plane, is represented by another linear equation. Not a surprise in linear algebra. And of course, we could rewrite this in the form 2x plus 1/3 y plus z is 5, just by moving all the x and y stuff to the left and keeping only the constant at right. That is analogous to the sort of thing we saw with the line, except now there's an x term, a y term, and a z term. And guess what? There was nothing special about this plane. The fact that it cut through the z-axis at 5, that it had an x slope of -2 and a y slope of -3. Replace this 5 with any number you like, replace this x slope with any number you like, replace this y slope with any number you like, and you still get something of this basic form, only those numbers will change accordingly. And the moral of the story is that any plane in R3 can be represented by an equation in 3 variables now of the form ax plus by plus cz is some constant d. And I'm not even worried about assigning meanings to a, b, c, and d. I just want you to see that corresponding to this plane in 3 dimensions, we have a linear equation in 3 variables. And all we used in either of these cases was really that flatness of the figure. It's that flatness that gave us the slope of the line, or the 2 x and y slopes of the plane. Well, if we were to jump next to the equation of a 3-dimensional hyperplane in R4, I'll bet you can guess what it would look like. And you would be right. And you could justify it by the same kind of argument, even if you couldn't quite draw it. In R4, points, of course, have 4 coordinates. There are different conventions as to what to call them, but I'll call them x, y, z, and w. I know I'm going out of alphabetical order here, but I like to keep the x, y, and z in the usual positions. And the idea is that we could express w as a function of x, y, and z. And the flatness of our hyperplane, our 3-dimensional hyperplane in R4, would mean, geometrically speaking, that we would have well-defined x slope, y slope, and z slope. So for every unit we run in the x direction, the w coordinate would rise by a certain number of units. That would be the x slope. For every unit we run in the y direction, the w coordinate would rise by a certain number of units. That would be the y slope, and so on for the z slope. Put all that together, and you'd end up with an equation, something like, let's say w equals 8 minus 5x, if the x slope is 5, or rather minus 5, plus 4y, if the y slope is 4, minus 19.2z, if the z slope is minus 19.2. And you could shove those 3 terms over to the left, and you'd end up with this equation. It's a linear equation now in 4 variables, x, y, z, and w. And then we have that constant on the other side. And we could do that with any 3-dimensional hyperplane in R4, which means that we would end up with equations of the form ax plus by plus cz plus dw is some constant e, not obviously the base of the natural logarithm. So our 3-dimensional hyperplane in R4 is a linear equation in 4 variables. Of course, it's going to have 4 variables. It's in R4. We have to account for all 4 coordinates. Just like the plane in R3 is, of course, going to have 3 variables, and the line in R2 is going to have only 2. But they're all linear. And the important thing here is that you understand that the flatness of these objects means that they have specific slopes in specific directions, which in turn means that we end up with simple linear equations. And we are going to be dealing with linear equations very, very frequently in this course. So much so that many linear algebra courses literally begin just talking about linear equations, but that strikes me as being far too boring and giving almost zero insight into what's actually going on. But anyway, I think you can see how this progresses, and you should now be able to understand that if you see some linear equation, like this one, 2x1 minus 5x2 plus 3x3 minus pi x4 plus 7x5 is equal to 22, you should be able to say, well, it's an equation in 5 variables. That means its graph lives in R5. Moreover, it is a linear equation in 5 variables, right? This is just a linear combination of those 5 variables on the left-hand side equal to a constant. Because it is a linear equation in 5 variables, its graph is one of our famous flat friends. It's the kind of flat, infinitely extended object in 5 dimensions that's just 1 dimension lower. That means this would correspond to a 4-dimensional hyperplane in R5. That's a thing you want to be able to recognize. Doesn't really matter how this hyperplane is arranged in R5. We just want to know that's what it corresponds to geometrically. What we will be seeing when we get to chapter 4, for example, is we will often have situations where we get a bunch of equations like this, like say 5 of them. And that would correspond to 5 different 4-dimensional hyperplanes in R5. And we will think of the system consisting of all 5 of those equations. And we will be looking for points that satisfy all 5 equations in the system, which would be a point where all of the different hyperplanes intersect. And we will come up with an algebraic technique for finding such a point. And we will see many situations in which such systems of linear equations arise. 2 last things I want to say about this topic before we switch over to parametric equations. First, I realized too late that I brushed over something, I actually mentioned it, when we were talking about planes in R3. I said that just like in the case of R2, we could have a vertical line, which doesn't fit that point slope paradigm, but which nonetheless has an equation of this form. You could have the same thing with a plane in R3. The problem with the vertical line was that it didn't have a well-defined slope, and for that matter, didn't have a y-intercept. Well, you could have a plane like, say, this one, that is parallel to the z-axis. So it doesn't have a z-intercept, and it doesn't have well-defined x or y slopes. So that little argument we used before to come up with this equation wouldn't work in that case. Doesn't matter. This still satisfies this equation. The idea is that in this case, the z coordinate of any point is totally immaterial. All we have to do is find the equation of this line where it intersects the xy plane. Just think about it now as a line in R2. Come up with its equation. Let's just say for the sake of argument, it's y equals minus 3x plus 8, or if you like, pop that onto the other side so that we have 3x plus y equals 8. Well, guess what? The equation of this line, just thought of as a line in R2, is also the equation of the plane. Because once you know a point satisfies this relationship between its x and y coordinates, well, it doesn't matter what the z is. Every possible value of z works. For example, we can see that when x is 2 and y is 2, that equation is satisfied. And since there's no z in that equation, we could let z be whatever we want. The point 2, 2, 0 satisfies that equation. The point 2, 2, 1 satisfies that equation. The point 2, 2, 42 satisfies that equation. The point 2, 2, negative 118 satisfies that equation. Which makes sense because the plane is just the set of all points directly above or below the line. And of course, this still satisfies this equation. It's just that c, the coefficient of z, would be 0 in that case. And the same thing happens in all the other cases as well. The second thing I wanted to mention is someone might ask, well, okay, we've got a line in R2, a plane in R3, a 3-dimensional hyperplane in R4. It's always 1 dimension under the dimension of the ambient space. But what if we had, say, a line in R3, which is 2 dimensions shy of the dimensions of the full space? What would the equation of that look like? Well, that would be a dreadful thing to describe with Cartesian equations. You can do it, but it would require not writing down a single equation. It would require multiple equations. Like I could describe a line in R3 as the intersection of 2 separate planes, which would be 2 equations of this form. And so that's what I would need to specify a line in R3. Instead, something like this is very easy to describe with parametric equations, which is what I will turn to next. All right, so let's talk about how to write down a parametric representation of this line. And the first order of business is to get rid of this ridiculous object and replace it with something that looks a little more respectable. I've drawn this line in R3, but one of the nice things about the parametric approach, especially when combined with vectors, is that what I'm about to show you will work for a line in any number of dimensions. So let's get to it. The line, of course, consists of infinitely many points, and each one of those points corresponds to a vector. Let's go ahead and call this vector A, both because it's the first letter in the alphabet, and also because I want to think of it as a kind of anchor, a point that anchors us somewhere in space, and from which we will roam in both directions along the line. And speaking of direction, let's write down a vector, any vector, that is parallel to this line, like this one, which I will call B. Now, the point at the end of my first vector, the green vector, corresponds to vector A. But what about the point at the end of this second vector? To what vector does that correspond? Well, of course, it corresponds to this vector, which is the vector sum of A and B. So if you'll forgive me for abusing the notation a little bit, I will label that point as A plus B, and I'll go ahead and label that first point as A. Okay, so now we know for 2 points on the line the vectors that correspond to them, but it's easy to get the rest of them. For example, instead of adding B onto A, why don't we take an A step and then 2 B steps, which would take us to this point, which of course is A plus 2B, or at least it corresponds to that vector, which more properly looks like this. That's A plus 2B. Or I could get A plus B plus B plus B again, which takes me to this point, which corresponds to A plus 3B. And we can do the same thing on the other side of this line as well. If instead of taking A and adding B to it, we take A and subtract B from it, we end up at another point on the line, which corresponds to the vector A minus B. And of course, you could have A minus B again, which takes us to A minus 2B, or the point corresponding to it. And you surely have the idea by now. Every single point on this line can be reached by a vector of the form A plus some number of B vectors. It doesn't have to be a whole number of vectors. For example, we could do A plus 2.7 copies of B, which would take us somewhere around here. But every point on the line is of the form A plus something times B, and everything of the form A plus something times B corresponds to a point on the line. So that means we can actually represent that line in space as A plus T times B, where T is just a parameter. It can take on any real value you like. For all the different possible real values of T, you get all the different points on the line. Very nice, very simple, very compact. And this simple expression works in any number of dimensions. In R2, for example, if we have some line, we can come up with a parametric description of the line in the exact same way. Just start with any old point on the line, let A be the vector corresponding to it, take any old vector parallel to the line, call it B, and then every single point on the line will have the form A plus TB for some value of T. Here, for instance, this point is A. This point is A plus B. Then we would have A plus 2B over here, A plus 3B over here, A plus 4B. And on the other side, we would have A minus B here, and A minus 2B, and A minus 3B, and A minus 4B, and so on and so forth. And even if we're working in 100-dimensional space, and we have the origin of that space and a line in 100-dimensional space. Now, the space may have a very high number of dimensions, but the line is just a line. It's an ordinary one-dimensional object, and we can describe it in the usual parametric way. Take any old point on it to serve as an anchor, take any old vector that's parallel to it, and now all the points on the line will have the form A plus TB, where T is some real number, depending on where on the line it lives. This point, for example, is just plain old A. Here we have A plus B. Over here, we have A plus B again, so A plus 2B, or A plus B plus B plus B, A plus 3B is here, or A minus B is here, A minus 2B, etc. A minus half a B might be somewhere over there. So this parametric expression for a line, A plus TB, is very, very general indeed. Let's use it in a concrete case with some actual numbers. Let's suppose we have a line in R3, and we know that the point 2 minus 5 8 lies on the line, and we also know that the point 1, 0, 3 lies on the line. Now, we know, of course, from day 1 in geometry that 2 points suffice to determine a line, so that means there should be enough information contained here to write down our parametric representation of this line. Is there really? Sure there is. There's several different ways we can do it, in fact. What we saw before was that we need to start with some anchor point. Let's use this point as our anchor. So I want to think of the vector corresponding to it. And that vector is, of course, the vector 1, 0, 3. I'm using the usual vertical format for vectors that we'll be using in linear algebra. This is to distinguish the vector from the point. Anyway, we have our anchor, and now we just need another vector parallel to this line. Well, let's use the obvious one that runs from our anchor point to the other point we know, because then we can write down the coordinates of that vector very easily. So let's think it through. This vector goes from 103 to 2, minus 5, 8. So thinking of the vector in terms of displacements, what do I have to add to 103 to get to 2, minus 5, 8? Well, that's easy. To get from 1 to 2, I have to add 1. So the first component of my displacement vector should be 1. To get from 0 to minus 5 in the second component, I have to subtract 5. So the second component in my displacement vector should be minus 5. And to get from 3 to 8 in the third component, I have to add 5, which will be the third component in this displacement vector. And so now I've got it. The points on the line correspond to vectors of the form 1, 0, 3, our anchor vector, plus t times 1 minus 5, 5, which is that displacement vector parallel to the line. And again, don't just memorize this. You should just be able to think about this and it will be obvious. Think dynamically. We're starting at 103, our anchor point, and then we are just adding on copies of 1 minus 5, 5. And we could rewrite this expression as a single vector rather than as a linear combination of vectors like this if we just do the arithmetic. So now we have one single vector where the first component is 1 plus t, which is what we get when we do the scalar multiplication here and then do the vector addition. Similarly, the second component is minus 5t, and the third component is going to be 3 plus 5t. And in fact, another way we could express all of this is by thinking of our original expression as giving us the x, y, and z coordinates of a variable point on that line. So then we have x, y, z, that vector, is equal to this vector, 1 plus t, minus 5t, 3 plus 5t. And we could re-express this instead of a single equation where one vector is equal to another. We could write it as a set of 3 separate equations, 3 parametric equations, one for each coordinate. And if we did that, then we would just equate the first components and we would get the equation x equals 1 plus t. And then if we equated the second components, we would get the equation y equals minus 5t. And finally, by equating the third components in our 2 equal vectors, we would get z is equal to 3 plus 5t. So let me explain what I've done. Or rewriting this, all this junk, as a set of 3 parametric equations, we have this. When you're writing up your own work for tests, homework, whatever, you do want to make sure you are not just turning in scratch work. You need to explain in a phrase or two what's actually going on. So I will try to model good behavior here. And if you've had a course in multivariable calculus, you may have seen things like this already, or even in a physics class where you have a different equation for each component, whether or not you ended up thinking of them in terms of vectors as well. Except in those contexts, you might have had more complicated equations here. Here, they will always be linear. Anyway, we can use the parametric representation of our line, whether we think of it in this form or this form, to answer questions about the line. Like, for example, this line intersects the xy plane somewhere. What are the coordinates of that point where this line crosses through that plane? Well, that should be very easy to figure out. We can probably do it in our heads. I mean, the one thing we know about that point is since it's on the xy plane, then like every point in that plane, its third coordinate is clearly 0. But if the third coordinate is 0 and it lies on this line, well, go to the third parametric equation. When z is 0, what does t have to be? Well, solve that equation. 0 is 3 plus 5t, and you get that t has to be minus 3/5. So take that minus 3/5 and feed it back into these other two parametric equations. When t is minus 3/5, x is 1 minus 3/5, and therefore 2/5. Similarly, when t is minus 3/5, y would have to be minus 5 times minus 3/5, which is going to be 3. And so those would be the coordinates of that point. And of course, it makes perfect sense that this would correspond to a point where t is negative, because here was the point where t is 0, and here was the point where t is 1. And if we had our anchor plus 2 copies of our red vector, we get to a point where t is 2, and these would all be positive values of t. Back on this side of the line, these are where we would have negative values of t. But enough about lines. Let's move on to parametric representations of planes. So let's say we have a plane, and I've drawn it in R3, but this would work just as well in R4 or R5, and so on. We're going to come up with a parametric representation of it. What's going to be a little different this time is that we will have not just one, but 2 parameters. The reason for which will be very clear in a moment, because the process by which we'll obtain our parametric representation is almost identical to what we did for the line. So pick any old point on the plane that will serve as our anchor point. It corresponds to a vector, which I will call A. Now the plane is a 2-dimensional object, which is why I'm going to need 2 parameters in here. In particular, to reach every single point in the plane, I'm going to take 2 vectors parallel to that plane, and I will need them to be linearly independent vectors, as I have drawn them. Let me give them names. How about v and w? Well, think about the grid that v and w determine. It will, of course, pervade that entire plane, since the 2 vectors are linearly independent. And now I think you can see how we can come up with a representation for any point on this plane. This one, for example. How do we get to that point? Well, we can take an a step, a v step, maybe half of a v step, and then a w step. So put that all together, and that's a plus 3/2 v plus w. Or this point in the plane. How would we get to it? Well, we would take our a step to get us up on the plane, then a v step, then another v step, and then a minus w. So this point could be a plus 2v minus w. And I won't belabor the point, but I think you see that every point in the plane is going to have the form a to get up on the plane, plus some number of v's, plus some number of w's. So points on the plane correspond to vectors of the form a, our anchor vector, plus tv, our first parameter is the number of v steps we have to take, plus sw, where s, our second parameter, is the number of w steps we have to take. And note once again that v and w need to be linearly independent vectors on that plane. If they weren't, then they would lie on the same line, and things of this form would just be points on a line, because v steps and w steps would just be steps along the exact same line. Good. And as often as not, more often than not, in fact, what will happen is that we will encounter things of this form, and then we will be able to recognize, that is describing a plane, a 2-dimensional object. In fact, I mentioned earlier in this video that in chapter 4, we'll start looking at systems of linear equations, where we'll have a bunch of linear equations, and we will look for simultaneous solutions to all of the equations. And typically, we will end up finding them in some kind of parametric form. And so if we see something like this, we'll say, I've got a whole plane's worth of solutions. And in fact, we'll usually unravel such a thing from something like this. We will have solved some system of equations, and we will find our solutions looking like this, where x, y, and z all depend on 2 parameters, t and s. And we will think about that solution by rewriting it in vector form. Instead of thinking of this as 3 separate equations, we'll think of it as a single equation between 2 vectors. On the one hand, x, y, z, the left-hand sides of those 3 equations, and on the other hand, the vector whose 3 components are the 3 right-hand sides of those equations. And then this vector is something that we can decompose into a linear combination of simpler vectors, like this. We'll say it is the sum of the vector 1, 2, 8, the constant terms there, plus t copies of the vector minus 3, 4, 0, that's reading off this middle piece right there, plus s copies of 5, minus 1, 2, which we read right off of this one. And when we look at this stuff, we should recognize that as something of this form. I've got an anchor vector, and then I'm taking a certain number of steps given by this vector, and a certain number of steps given by this vector. So what I'm getting, as long as these two vectors are linearly independent, which they clearly are, what I'm getting is a plane. So you'll be seeing lots of that kind of thing in chapter 4, but to pave the way, you'll have homework problems similar to that in this chapter. A few more things I should mention. First, since this plane does not include the origin, it is not a subspace of R3, which we talked about in the last video, because every subspace must contain the origin. But it still feels kind of subspacey. It is still a plane in R3, it's just not a plane through the origin. Something like that, the result of taking a genuine subspace and shifting it away from the origin, is what we call an affine space. So it's just a subspace shifted away from the origin. We can't quite do linear algebra fully in such places, but they arise very naturally in solutions of systems of equations, so we do have a lot to do with them. Same goes, of course, for a line that does not include the origin, that would be an affine space, or a hyperplane that does not include the origin, that would be another affine space. So nothing deep there, just some terminology. Although maybe I should note that if we were working not with an affine space, but with an honest-to-God subspace, say a plane through the origin, the difference we would see in our parametric representation of it is that we wouldn't actually need an anchor vector. We wouldn't need to step up to the plane. So that could be thought of as the zero vector. We could just take any two vectors in the plane that were linearly independent and just have TV plus SW, and we would get everything we need that way. Okay, we have pretty thoroughly discussed the parametrization of lines and planes, but what about hyperplanes? Well, I have a feeling you know how that's going to go without my even having to say anything about it. It will look exactly like the line and plane cases, except that we will need more parameters. For instance, suppose you were to encounter something of this form: vector A plus T1 copies of vector V1 plus T2 copies of vector V2, so on and so forth, up to T8 copies of vector V8. What could we say about such a thing geometrically? Well, the first thing we would want to know is, are these vectors linearly independent? So let's suppose we know that the VI's are all linearly independent. Again, down the road, we will learn some specific tests for linear independence. But for now, let's just take it as read. Anyway, should we, in our linear algebraic wanderings, come across an expression like this, where we know those 8 vectors, V1 through V8, are linearly independent, what can we say about this thing geometrically? What does it represent? Well, the 8 linearly independent vectors span a 8-dimensional hyperplane. Their linear independence guarantees that. Each one of them contributes another dimension to the span. And what's this initial vector A doing? Well, that's like our little anchor vector. It's as if in whatever dimensional space we're working with, it's got to be at least 8. We're going to start from the origin, step up by vector A onto this 8-dimensional hyperplane. And that's that. So we know, roughly speaking, what this thing represents geometrically. Now, what if the 8 vectors were not linearly independent? Like, what if the vector V8 lies in the span of the first 7 ones, which are linearly independent, let's say? Well, then in that case, this would correspond to a 7-dimensional hyperplane. Or if all 8 of the vectors were parallel, in that case, this would be a 1-dimensional object, a line in whatever space we were working in. Let's finish this off with one more concrete example. Let's look at this set of 4 parametric equations where we have 3 parameters, S, T, and U. And again, this is the sort of thing that could come out in the wash when we're solving a system of linear equations, as we'll see later, which in fact is why we're doing all this stuff now. But be that as it may, let's say we encounter this and we want to interpret it, if we can, geometrically. Well, we have parametric equations for 4 variables, so we know that we're operating in 4-dimensional space. And it will be easier to see what's going on if we rewrite this thing in vector form, so that we don't have 4 separate equations, we just have a single equation with vectors on either side. And if we do that, then on the left side, we would just have the variable vector, whose 4 components are x, y, z, and w. And on the right side, we would have the vector whose components are the right sides of those four equations. And then we could take that vector and decompose it into a linear combination of simpler vectors. And I did that on an earlier example, and I have a hunch that if you've come this far with me, you will be comfortable with writing down the decomposition all in one shot from the original. Let's see. If we do that, we would end up with all the constants being a vector. So 2, minus 3, 0, 9, our vector of constants. Don't forget the 0, which doesn't appear in that equation, plus s copies of some other vector, namely the vector whose components are the coefficients of s in our four separate equations. So that would be the vector 5, 1, 0, and 0. Then we would have to add t copies of the vector of the t coefficients, which are minus 1, 1, 1, and 0. And finally, plus u copies, our final parameter, of the vector of coefficients 1, 3, 0, and 6, drawn from the u's in our four equations. Well, now we're in business. This looks like something we can understand, because look at this stuff we've got on the right-hand side. We've got our anchor vector, and then we've got the span of three other vectors in R4. Well, the span of three vectors, that could be as much as a three-dimensional hyperplane. So this whole thing could be a three-dimensional hyperplane, or something of lower dimension, depending on whether or not those three vectors are linearly independent. And I've actually designed these so we can figure it out pretty easily. So let's think about the first two vectors, 5, 1, 0, 0, and minus 1, 1, 1, 0. It's obvious that those are linearly independent, because the only way two vectors can fail to be linearly independent is if they are scalar multiples of one another. Those are not scalar multiples of one another. So of course, those two are linearly independent, which means that this whole thing represents at least a two-dimensional plane and at most a three-dimensional hyperplane. The only question is, does this third vector lie in the span of the two that precede it? And even though we cannot see these things, because these are four-dimensional vectors, it's very easy to see that this one does not lie in the span of those two. We can see that by thinking about their final components, 0, 0, and 6. There is no way to take a linear combination of the last two components and come up with 6. Any linear combination of the last two components is 0. So no linear combination of those two vectors could possibly give us this vector, simply based on thinking about their fourth components. As a result, we know that these three vectors are linearly independent. That means that this stuff right here corresponds to a three-dimensional hyperplane in R4, a subspace, in fact. Of course, it contains 0, because if we set s, t, and u all equal to 0, we would get 0. But we have this anchor vector. It's like we step up to the hyperplane. So the hyperplane is shifted away from the origin. So it is, to use the language I introduced earlier, an affine space. But more fundamentally, all this stuff corresponds to a three-dimensional hyperplane in R4. And I think that is about it for this video, and indeed for this chapter. So make sure you do all the homework problems, and I will see you next time when we begin Chapter 3. Hasta luego.